Hello students, hope you all are good and welcome to the physics class. Today's topic of discussion is applications of Gauss's law. The learning objectives of the topic are, after the completion of the topic, students will be able to find the electric field of two parallel charge plates using Gauss's law and to derive the expression for electric field due to a charged spherical shell using Gauss's law. Now dear students, you are familiar with the electric field intensity due to a single charge sheet. In the previous lecture, we came to know that the electric field due to a single charge sheet is E is equal to sigma upon 2 epsilon naught, where sigma is surface charge density of the sheet and epsilon naught is the permittivity. Now, today's topic of discussion is to find the electric field intensity due to two parallel plates having surface charge density sigma 1 and sigma 2. So consider here that two charge sheets are there having surface charge density sigma 1 and sigma 2, and let us consider that the surface charge density sigma 1 is greater than surface charge density sigma 2. Now first of all, we have to consider the direction for electric field intensity. Since the two plates are positively charged, therefore electric field intensity will be radially outwards. Now let us consider electric field intensity due to first plate. Now this is first plate, the electric field intensity will be radially outwards. So it will be along this direction also, it will be along this direction also, and it will be along this direction also. Similarly for second plate, that is the plate which is having surface charge density sigma 2, the electric field intensity E2 will be again radially outwards, and the direction for E2 will be perpendicularly outward in this direction, perpendicularly outward in this direction, and also perpendicularly outward in this direction. Now, let us consider the region 1. In region 1, you all can see the direction of E1 and E2, it is acting in the same direction. Hence, the electric field intensity will be E1 plus E2 because these are collinear vectors and hence they will be added up, and the relation will be E is equal to E1 plus E2, and simply we will add. The electric field intensity due to first plate will be sigma 1 upon epsilon naught, and the second will be sigma 2 upon 2 epsilon naught, and it will be simply added up. Now, let's consider the third case. In the third case also, look, the electric field intensity, it is acting in the same direction, that is E1 and E2 are in the same direction, and again it will be simply added up. That is E net will be equal to E1 plus E2, substitute the values and we will get this answer. Now consider region 2. In region 2, E1 and E2, they are acting in the opposite direction, and we have considered that sigma 1 is greater than sigma 2. Since they are in opposite direction, therefore the net electric field will be E1 minus E2, and substituting the value we will get this relation, that is sigma 1 minus sigma 2 upon 2 epsilon naught. Now let's consider one more case, that is when the two plates, they are having same charge density but oppositely signed, that is one plate is having plus sigma and the other plate is having minus sigma. Now by using the same concept as previous, first we will give the direction for electric field intensity, that is for first plate it will be E1 along this direction, E1 along this direction, and similarly along this direction, that is radially outward. Similarly for second plate, we will give the direction for electric field intensity, that is E2, and since it is negatively charged, therefore the direction will be radially inwards. You can have a look. Now it is in the inward direction. This. Now consider the case for first region, that is region 1. Now look here, in the first region, E1 and E2, they are in the opposite direction. Since they are in opposite direction, therefore the net electric field will be E1 minus E2. Substituting the values, we will get the answer 0 because surface charge density in both the cases is same. That is sigma 1, sigma 2 is equal to sigma, but they are in opposite sign. Similarly, in the third case, that is third region, now both are acting in the opposite direction. E1 and E2, they are in opposite direction, and hence the net electric field will be simply added up but in opposite direction, and hence we'll get the answer 0. Now in second region, the net electric field will be E1 plus E2, because you can have a look, E1 and E2, they are acting in the same direction, and therefore it will get added up, that is E1 plus E2, and when we'll substitute the values, we'll get the answer sigma by epsilon naught. So what is the conclusion over here? The conclusion is that when we have two parallel plates which are having same surface charge density but opposite in sign, then the net electric field outside both of them is 0, but the net electric field inside the two parallel plates is sigma upon epsilon naught. So this is a very important concept. I hope it is clear. Now let's come to the next application, that is electric field intensity due to a uniformly charged thin spherical shell. Now we are having a shell, that is a hollow sphere we are having. So consider here first of all a hollow sphere whose radius is capital R. You can have a look over here. This is a hollow sphere whose radius is capital R. Now, which is positively charged. This hollow sphere is positively charged. You can have a look over there. It is positively charged. Now, we will find the electric field intensity in the three regions. One will be outside it, the other will be inside the hollow sphere, and the third will be on the hollow sphere. So let's consider the first case, that is the point is lying outside the shell. Now applying Gauss's law, that is E ds is equal to q upon epsilon naught. Now first of all, what we have to consider? We have to consider a hypothetical Gaussian surface. Now this we will consider a hypothetical Gaussian surface outside this shell having radius small r. Now electric field intensity will be radially outward because it is positively charged, and this small surface ds, we are going to consider its direction will be again perpendicularly outward. Since both are in the they are in the same direction, and hence EDS will be EDS cos 0 and it will be EDS. So E being constant will be taken out, and the integration will be on the small surface ds, and the surface area will be 4 pi r square. So substituting the value over 4 pi r square, we will get the electric field intensity over here. E is equal to q upon epsilon naught r square. Now since we are aware of that, the surface charge density is given as charge per unit area. So q will be sigma into 4 pi r square. Substituting the value of q over here, we will get electric field intensity to be sigma r square upon epsilon naught small r square. Now let us consider the second case, that is when the point A is on the surface of the shell. That is, now we are going to consider the point, observation point, to be on the shell. Now again applying Gauss's law, since electric field is radially outward, ds we have taken, it is radially outward, perpendicularly outward, so both are in the same direction, it will simply EDS, which is equal to q upon epsilon naught. Again integrating over the whole surface ds, we will get 4 pi r square, because r is the radius of the sphere, the given sphere, charged sphere. So it will be E into 4 pi r square q upon epsilon naught. Substituting the value, and we'll get E is equal to q upon 4 pi epsilon naught r square. Now again substituting the value for surface charge density, we will get E is equal to sigma upon epsilon naught, which is a constant. Now let us consider the third case. The third case is when the observation point is lying inside the shell. Now our problem is that our observation point is inside the shell. Now we will consider a Gaussian surface again over here. Again applying Gauss's law, EDS, they are in the same direction, so EDS is equal to q upon epsilon naught. Now here simply no charge is there inside the surface, and simply Q here will be 0 since Q is 0, and hence E will be simply 0 over here. That means no electric field intensity will be there inside the shell. Now, if we plot a graph for these three given conditions for the hollow shell, we'll consider that E along this direction along y-axis and the observation point along this direction, that is x-axis. As we have seen that inside the shell, that is up to R, the electric field intensity is 0. Therefore, will not get anything there. And after that, at R, in the previous case we have seen that at R the electric field intensity is maximum. Therefore, we'll get the answer from here, that is from this point. Electric field intensity is maximum at point R, and then after that, as we are moving away from this shell, we have seen that electric field intensity is inversely proportional to R square, and hence it will decay like this. Electric field intensity will decay like this, and hence the graph is like this. So I hope the two applications are clear to you, and kindly go through that, and next we are going to solve the numericals regarding these relations. Thank you. Have a good day.